Hello, good morning. Welcome back to another mathematical technique in chemical kinetics. It is the determination of order of reaction. The order of reaction is an experimental determination where the rate expression says the value of n is the order of the reaction. This value, which we cannot evaluate by any theoretical concept, no theory to evaluate the value of n. It is an experimental evaluation. Let us see how it is experimentally evaluated for different reactions. There are four methods. We have written three methods over here. All these three methods are applicable for a simple reaction like this. First step is to know whether the reaction is in gas phase or liquid phase. That is, the reaction is whether in the gaseous state or in the liquid state. Then we need to set up the reacting system, reaction vessel, and other equipments and their arrangements to monitor the concentration of the reactant at different interval of times. It is a scientific approach. It is a scientific research as well to design the reaction, that is to design the reaction vessel and its equipment for measurement of the concentration of reactants or products at different times. Of course, these equipments or arrangements may be different for different reactions. Once this equipment or setup is ready, design is ready, you go for measurement of values, experimental values. Take the reactant and monitor the concentration of the reactant at different times. Measure the concentration of the reactant at different times. How much reactant or how much remaining. Record the values. Record about 10 to 15 values at different times and tabulate them like this in tabular column. Recording of values, observation of values, recording of values and tabulation of values. Tabulate them as like this. This is T, this is value of X, this is value of A minus X. X means concentration of the reactant reacted and concentration remaining. The time is at different time. The T equals 0 means at the commencement of the reaction there is no change in concentration. Reactant is not yet reacted. 0. Concentration A minus X is A. That is the initial concentration of the reactant A. These values should be known. At every time now T1 or T2, regular interval of times. After T1, after T2, after T3, record the corresponding values. What are the values of X? Like this, or A minus X, remaining concentration like this. The timings, you may take 1 minute, every 1 minute, or every 5 minutes, every 10 minutes, it depends on the velocity of the reaction. Interval of time. Record those values and tabulate them. This is the tabulation of the values. Then go for calculation. What is the calculation? We have already know that expression. 3 different expressions we have derived for 0 order, first order and second order. This is a trial and error method. Take the equation one by one and verify which equation it obeys. Which equation holds good for the reaction? Take this equation for zero order. K equals x by t. X and t are variables, but ratio remains constant if the reaction is zero order. You have to check. That is, for at different times calculate the value of k. K equals x1 by t1 for this set of values. We don't require for this in this case. Calculate k on different times. x2 by t2. K, x3 by t3. Like that, all the values you have recorded now. Calculate the value of k. If the value of k remains constant, if the value of k found constant, then the reaction is zero order. If the value of k not constant, the reaction is not zero order. Verification of this equation. If this is not constant, then try with the next equation. Next equation is first order equation. This is one. Here also we have values of x, values of t, values of a minus x is there. So in the similar way, calculate the value of k at different times. K equals t is t1, x equals x1. A value is this value. Calculate the value of k at this time, value of k at this time, value of k at this time, t3, x3, and different values, and see that if the value of k remains constant, then this equation holds good for this reaction. This obeys the equation like this. It is a first order reaction. If it is not, try with the next equation. The next equation is second order equation. Recall the equation. This is the equation we have derived. The same way do the calculations for k at different times. Like this, and see that if the value of k found constant, it is a second order reaction. It is a trial and error method. You have to calculate, take different equations and calculate and check and find out which equation, which among them the reaction obeys. Trial and error method. If this reaction obeys this equation, it is first order. If this obeys this, zero order, first order and second order. But no reaction obeys two equations, only one equation obeys. So this is how we can find out the order of the reaction by trial and error method. First method. And in the second method is also called differential method. What is differential method? A graphical method. We also called graphical method or differential or instantaneous differential equation method. With the same set of values, what you have recorded in experiment, these values and these values. This value a minus x is also called as a concentration of a at different times. Another symbol, of course. These are time intervals. At different times we have recorded concentration of the reactant remaining at every instant. Take these values, set of values, and put them, see them in the graphical form. Draw the graph for these values, that is a minus x and t. We get a curve like this. This is a curve already shown out. Reactant concentration decreases with time. From the graph, we can find out the rate of the reaction at two different concentrations. Any two rates I want, because we can calculate number of rates, number of instantaneous rates. So any two rates of reaction. For that, take any 2 points on the curve. This is one point I have taken, another point. Draw a tangent to this point. Find the slope. What is slope? Tan theta. Let us call this as angle as theta, tan theta 2. So this tan theta is the slope or rate of the reaction. Instantaneous rate of reaction at concentration A2. This point has some concentration because concentration values. At this concentration, this is the rate of reaction. Directly, what is that? The value we see in the graph. Calculation like this. The similar calculation we can apply at this point. Try a tangent, find the slope. angle theta, the tan theta is equal to rate of the reaction at this concentration. This point corresponds to this concentration. So these values are known. For this concentration, this is the rate of reaction. For this concentration, this is the rate of reaction. Knowing that, we can go for evaluation. Take the same equation, R is equal to K divided by 4 of N. And look at this. So for two sets of values, rewrite the same equation. When A equals A2, rate is R2. When A equals A1, concentration is A1, rate is R1. Substitute them, these are simultaneous equation. Divide one by the other. Left hand side by left hand side, right hand side by right hand. K cancel. That is A2 by A1, whole raised to the 4 of N. Knowing this value, knowing this value, knowing this value, knowing this value, take the ratio as some value. If value of the ratio is P, a known value, the value of this ratio is something like this Q, known value, we can evaluate the value of N mathematically. What is that? So take log, because explain now. Take log on both sides. That is, explain is N into log of this. N is equal to log P divided by log Q. Knowing this value, take the logarithm of this value, logarithm of this value, and divide them, you get the value of N. Value of N is the order of the reaction. That is the differential method, differential equation method, or graphical method like this. The same set of values, either you follow this trial and error method or a differential method like this. And the third method, it is the half-life period method. What is that half-life period reacting system? Again, we need a scientific approach, scientific research approach to what is that. So set up a reacting system, reaction vessel, and what is that, equipments to measure the half-life of the reaction. We need what is that, the instrument, or what is that, additional equipments for the measurement of what is that time required for change in the concentration of the reactant to exactly half of the initial concentration. So there must be what is that, some experimental measurement. When the concentration of the reactant becomes exactly half of it, the time required, direct measurement, that is T off. This experiment is repeated for two different initial concentration, because when the concentration of the initially at the commencement of reaction, if you have taken some concentration, that is A1, that is half-life for this concentration, same reaction is T1. If you have taken the initial concentration A2, initial concentration different A2, and half-life for this concentration is T2, same reaction. Then using these set of values, recall this mathematical expression in the previous class. What is that? Half-life of a reaction is directly proportional to A to the power of 1 minus n, where A, that is half-life, is depending on what is that? Initial concentration and order of reaction, like this mathematical relationship. So using this, what is that? For these set of values. So when half-life is T1, initial concentration is A1. When half-life is T2, initial concentration is A2. For this initial concentration, half-life. For this initial concentration, half-life. That is, we have measured experimentally. Then simultaneous equation, you can take the ratio like this. So knowing this, these values are known. If the ratio is L, if the ratio is H, same N, we get like this. So evaluation is taking log on both sides. Log of this is equal to exponent into log of this. So 1 minus n is equal to this divided by this. N equals, take this to this side, n equals that side. N equals 1 minus of log L minus log H. So knowing all these values, the value of n can be calculated. This is half-life measurement. Half-life, what is that? Change for half-life. Change for half-life. So experimental determination. These are the methods applicable only for a reacting system, which is a simple reacting system like this. This is trial and error, differential method, and half-life period. The concept is this evaluation. Thank you. Shall continue.